Hello and welcome to 6.4, Volumes of Solids with Known Cross-Sections. This is AP Calculus BC. My name is Mr. Green, your teacher. Today, we will find the volumes of solids that have cross-sections between two functions. We'll talk about what that means in a minute. I kind of didn't state it very well. But for a quick review, let's go to the internet. So I stole this worksheet off of the internet, and it's just wants you to calculate the volume of these solids. Now, I really liked this worksheet because it gives you the area of this face. And if you know the area of this face, you can just times it by the height and find the answer. So this one, the volume of this shape is just 80 centimeters cubed. You just times these things, you have the answers. Times these things, you get the answers. You do that on like all of these. And that's basically the theme of today, but we're going to do it with integrals and shapes that are not uniform as they increase or decrease. It's going to be great. So let's talk about what that means. For cross-sections of area A of x, so this means the area of the shape, so that was the shaded region that we just saw, taken perpendicular to an axis. So there's two different things that we're going to deal with in this class when they're perpendicular to the x-axis and the y-axis. And notice the only difference between these two formulas is this in terms of d of x, and this is in terms of d of y. So that's why there's a and b here and c and d here. I decided to choose different letters. So the first one we will have is we just have to put a of x in here because this represents the height of our three-dimensional object. So we just need a of x in here. That's great. And this one will need a of y. Now, we get to review some things. So it's going to be quite helpful for us to know the areas of the following simple shapes. So, and I'm going to use S for like side length. So if this is S and this is S, then the area is S squared. Easy work, right? And then, like, you know how to do this one. If this is S and this is S, that means it's 1/2 base times the height. So 1/2 S squared. Now, it'll get a little bit interesting if we have this one as an S, because then we don't know the height. But we do know that these two are the same, and that means that this has to be a right angle. So that's pretty cool work right there. If that's a right angle, what other things can we figure out? Well, that means that this is 45 degrees and this is 45 degrees. So that means this is half of an S and this is half of an S. So the height of this triangle is just half of an S. So if I wanted to figure out the area of this one, I need 1/2 times the base times the height, which is S over 2. So I could have 1/4 times S squared. That's pretty crazy, right? Now a rectangle with height twice the base, so if this is S and this is 2S, then the area is just going to be 2S squared because we times them together. Now this is a cooler one, the equilateral triangle, and I forget it every single time I do this, but if we label these all as S, 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 and then that means that this height right here is what we have to figure out. Well, this is 60 degrees and that's 30 degrees. So that means that this will be square root of 2, or square root of 3, all over 2 times the S. So the height on this one is square root of 3 times 2 all over S. When you're probably like, Mr. Green, why? What's a 30, 60, 90? And so if this side's 1, this is square root of 3, and this is 2, but I have S over 2 here, so I had to times it by square root of 3 to get this side. So that means the area of this is going to be square root of 3 over half times a half is a 4th, and S squared, because S times S. Pretty cool stuff. And then A is equal to, if you have a semicircle, and this side right here is S, this is the crazy thing, you're going to have to half it. So this is S over 2. Because it's pi r squared, but then S is half of the radius, so we will get 1/2, because it's half of a circle, times pi times the radius, which is S over 2 squared. So yeah, that's as far as I want to take that one. We can solve it later, but it's pretty pretty cool looking. Like I could go 1/8 and all that, but I'm not going to remember it. So let me show you some of these solids, and I have a GeoGebra demonstration that'll kind of help us see what we're doing and what we're talking about when I have these volumes of solids. Okay, so I'm on GeoGebra. It's pretty cool. And what I have here in blue is I have the graph of y equals x squared, and I just put that in a three-dimensional axis right here. I didn't make this, I stole it off the internet. And then I have square root of x right here, and I put that right here. So what we're going to do is notice that we have these cross sections, which are squares. So each one of these is a square. And the length here in between these is the side length. And so I can increase the squares, and so we'll get this weird looking shape right here. And then the more shapes, the more cross sections we get, the closer and closer we get to an actual solid shape. So that is why we can use integrals on this. Isn't that cool? And we can look at it from different angles. For the majority of these questions, the bottom will always be flat because that's where your cross sections lie. And so it's just poking out of the shape. It's kind of cool looking. It's hard to visualize, right? And then I can show you some other shapes. So let's reset the thing. And let's talk about it if instead of squares, I put an equilateral triangle in here. So I could put a triangle in here, and we just talked about how to find the area of that triangle. And so we can create a shape like that. And notice that each one of these cross sections is just an equilateral triangle. Pretty cool stuff. Another option I have is semicircles. So if I put it up here like this, so if I put semicircles all the way through, and then I increase it to infinity, we'll get this kind of shape. Notice the bottom is flat. So those are the main shapes that you have to deal with on the AP test. Let's go back to our notes and let's try some of these. I'm so excited. The most difficult thing about doing these is going to be finding the area of those shapes. So find the volume of the solid whose base is bounded by the graphs of y equals x plus 1. That's a nice, easy graph to graph. I'm going to go ahead and start graphing it right now. And then y equals x squared minus 1. With the indicated cross sections taken perpendicular to the x-axis. That's a quite important wording right here, perpendicular to the x-axis. That tells us that we are going to be using dx. Okay, keep that in mind. I'll be right back with my graphs. Okay, so I had my graph. Sorry I had to go off of the axis. I wanted to zoom in. I zoomed too far. Anyway, so this is the shape of the thing that we have, and it's all enclosed, all of this. It's all enclosed right there. That's great. Now the first one we have to do is we have to find squares. We have to put squares in here somehow. And the way we're going to do that is we have them perpendicular to the x-axis. So that means here's the x-axis. I have them at right angles with the x-axis. So that means my cross sections are all going to look like that. And if you remember from a couple lessons back, that means just the height of this thing. And the way that we find the height is we subtract the upper function minus the lower function. So I can come over here and say the side length is just the upper function, which is x plus 1, minus the lower function, which is x squared minus 1. So that's the side length, and we can solve it and make it look all nice if we want. So that's great. We know the height now of this thing, and that's the side length of a square right here. Now I could try to draw a three-dimensional square coming out of here, but art is not my I was a math major, not an art major. I think I did pretty good. So that means this is S and this is S. So if I wanted to find the area of that, I just times them together. So I'd have this thing all squared, which is great. So the only problem is if we were going to try to do an integral with that, we don't know their intersections. Well, we do actually, because this is at x equals 1 and this is at x equals 2. So we're going to have the integrals from 1 to 2 on these, and so let's try to set one up. On this first one, we know that the area of the squares would be the side squared. So all I have to do is take the integral of -1, I definitely said -1 right here, right? And all the way to 2, and then I have to take that height thing and square it dx. And finding this out will give me my answer. I'm feeling extra lazy, so I'm going to use my calculator. All right, putting that in my calculator, I got 8.1. Once again, we weren't given units, so we don't need to put units, but the units on this would be whatever units cubed, because we're finding the volume of it. Notice I put an A here. That was a silly thing to do. I always do that for some reason. I write A when I mean V. Okay, now what I want you guys to try to do is I want you guys to see if you guys can set this one up. I'm going to set it up, and I'll come and show you what my setup looks like in just a second. So try this one. Go. All right, so this is my setup I got. I noticed it was just twice the width of the interval. And so I just took this and times it by 2, and then I ended up with this times this is just this 2 times this squared, and that's my setup. So I don't even need a calculator because I did this one, and I know that the answer will just be 16.2. That's great. Okay, now let's go ahead and try it with equilateral triangles. And remember, the formula for equilateral triangles is just right here, so we don't have a whole ton of work to do. Let's see if you can get this set up. I'll be right back with my answer and everything. Go. All right, shoving that in, I got 3.507. So that was pretty fun. I just took my answer from A and multiplied it by this because it's the same thing. All right, now we're on to the more fun questions. I just have 4-something questions that looked pretty interesting. So we're going to try them out and see what we can find out, and I'll have you guys try some. I want to work through this first one with you. It says the volume of a solid whose base is the region bounded by this circle x squared plus y squared equals 9, so the radius is 3, with the cross sections taken perpendicular to the x-axis, so that means we're going to be using dx, are isosceles right triangles with the hypotenuse lying on the base of the circle. Whoa, I gotta draw this thing. Now this question ended up super tricky because this is what I kind of drew. I've got lots and lots of these isosceles triangles on here, but the interesting part of this, something I could do here is I could say this is y and I could say that's y. And if I do that, I know that the area of one of these isosceles triangles is just going to be 1/2 times base times the height. So that's pretty good. Now, because it's an isosceles triangle, and we already figured that out, that means the height of this part will also be y. We talked about that up above. And so that means we have the area is just 1/2 times 2y times y. So the area is just y squared. And if we take our original function here and we move this x squared over there, then y squared is equal to 9 minus x squared. So that's pretty crazy. So the area is just equal to 9 minus x squared. That's really cool. So let's try to set up this volume here. We know that it's the integral from -3 to 3, so we could say the integral from -3 to 3, and then we could just have this 9 minus x squared and dx. That's all we need, because that's it. That's all we need. Now, that's a kind of annoying integral, because what I could do is I noticed that this was symmetrical here and here. So instead of saying -3, because this is an even function, I could say 0 and put a 2 here. That makes my life much, much better when I'm solving this integral. So what I'd like you guys to do is go ahead and solve that integral. You don't need a calculator for this one. This one's kind of an easy integral. And I'll be right back with my answer. I kind of ran out of room, but I got my volume is equal to 36. Pretty cool question, right? There's a couple cool little tricks that we can use like that. So what I'd like you guys to do is I'd like you guys all to go ahead and try this next question right here. So let R be the region bounded by the graphs of x equals y squared. What the trickiness. And x equals 9. Find the volume of the solid that has R as its base if every cross section is a semicircle perpendicular to the x-axis. So go ahead and draw the picture. And I highly recommend this y strategy on this one too. You'll see why. Anyway, Pretty fun stuff. Try it out. I'll be back with my solution in a few seconds. All right, I thought that was a great crazy question. I put a y here and a y here to, well, it should have been a negative y, but it doesn't matter. It's a radius, so it's positive. It doesn't matter. And then I said the area is pi over 2 times the radius squared, and then I was like, well, the radius is just 1y, so it's y squared. And then I noticed that y squared is equal to x, and I was able to integrate after that. It was a nice little happy integral. Crazy, crazy questions, right? Okay, let's try this next one. Let's see if you can get this set up and do this question. The tricky part with this one is it will say perpendicular to the y-axis. So in this question, we don't use dx, we have to use dy. So let's go ahead and see if you can do it. Make sure to draw a nice little picture and have fun. All right, so this is how I did it. I said, well, this is in the x direction, so my equilateral triangle will all have x's. You could have also just solved for the x and had an equation, which is 6 minus 2y. That would have been fine too. And said 6 minus 2y is this function, so that's clearly the height of this, the side length of that. Anyway, I got 9 squared to 3. I thought it was fun. And we're on to the last question of the day. These are quite tricky, right? So what I'd like you guys to do is I'd like you all to go ahead and try this one. It's a little bit tricky when you draw the pictures. Well, guess who made a typo again? Let's change this to a 2. It'll make our lives much better. All right, that was a tricky, tricky one because we had to have 2 different integrals, because if you notice, the top and bottom function, which is this one, it changed right here. So that was kind of crazy. So I had to change up which one was my top and bottom. Anyway, really glad we changed it to 2 right here. Yeah, I thought that was a good one. Okay, so practice 6.4 is on Delta Math. P.S. I don't think that these, it was 10, but then I changed it to 7. Questions will be enough, so I will attach an optional worksheet. The reason I say that is on Delta Math, we only have problems that are perpendicular to the x-axis, so you always use dx. But that's all the options they have, but I still wanted you to see the cool animations because they are really cool. Let me show you one. All right, so this one, you had to use square cross sections, and it was from 0 to 7. And so if you check out the slider, you can see that the integral is the accumulation of infinitely many squares that all turn into a solid that is made up of squares. Isn't that cool? Let's show you one with a rectangle, and I'll show you one of each. They're just so cool, you know. Oh, this is little tiny rectangles. But yeah, play with this slider because they're so fun. You'll only have to do 7 of these questions, and that's it. So have a wonderful day. Have fun on your practice, and I highly recommend you practice this a little bit more. Okay, talk to you later. Bye-bye now.